Okay, so the Pacific saury is mainly distributed to the distributed offshore in the Japan and the high sea of the North Pacific Ocean. So according to the so you can see according to the map of the CPU data, so you can see that the higher CPU is distributed in the offshore of Japan and the high sea. Yes, but unfortunately, its current status of this species is not good. So based on the historical catch, you can see that in the recent year, the total catch is decreasing and continue decreasing. And this fishery is harvested by the variable fleet like the China, Japan, the Taiwan, Russia, Korea. So this is a very important fishery in the North Pacific Ocean. And according to the biomass survey and the joint CPU index, you can see that the trend is decreasing. So the NPFC is one of the IFMO to monitor these species, and they raise the concern about this status of these species, and they want to improve some methodology for the star assessment and the abundance to improve our understanding of this fishery. So also this is the outline of my presentation. So this presentation will cover some practice for evaluating the spatial treatment in the CPU standardization, because we want to understand and improve our standing to the Pacific saury index, and assessing the star recruitment relationship, which is the resilience using the data from the Pacific saury fishery. And I would like to share the two topics. One is evaluating the spatial treatment on the CPU standardization. And in this topic, I explore how different spatial treatment affect the CPU standardization. And this including both the practical insights from the real fishery data and the simulation analysis. And the second topic, I want to assessing the star recruitment resilience, which is the stiffness, by using the biological data. Yeah. So let's move on to the first topic. So sorry. So as we know, it is important to recognize the sorry the CPU data might not always reflect the fish abundance, because we have several factors other than the fish abundance can influence the CPU data. And these factors often link to the spatial effect. For example, the CPU data could vary between the inshore and the offshore, and with the different vessel size. So we can account for the area effect to separate the different catchability among the different area. And the second, we can consider the preferential sampling, because in the fishermen cannot do the random sampling. They target the area with the higher fish density. So we can use the area stratification to identify the different area with the different fish density. So the area stratification is the common approach to address the spatial heterogeneity in the CPU standardization. So in the most common method for the understand the CPU, we just use the very simple statistical linear model to summarize any combined relationship of the many factors. And in general, we use the spatial heterogeneity in the fish density is treated as the area effect. So we can write down the very simple model. So this model can including the year effect, vessel effect, and the area effect. And we can predict the annual CPU by fixing the all covariance other than the density covariance, such as the year and the area effect as the density covariance, to predict the annual CPU. But this is the problem that is how to determine each area strata, which means how to define and how to determine the area stratification. So this is an issue for the area stratification for CPUE, and we have a lot of the approach to create the area strata in the CPUE data. For example, the ad hoc approach. So we just based on the very simple use the distribution of the CPUE data, and then we just use our eye to to separate the full area just based on the cage data or the CPUE data. So this is a most simple approach, but there is no guarantee to let the selected area stratification lead the unbiased index of the abundance in this process. So this study proposed some other area beside the ad hoc approach. We proposed some other area partition approach. The first one is the binary approach. So this approach is the automatic stratify the area depending on the model. So you can see the GIF, you can see that we can separate our spatial domain into the different area based on the fixed spatial resolution, and then we can use the for example, GL and to select based on the AIC value to select the best area stratification. Yeah, so we can continue to do this process. Yes. And the second approach, I use the spatial clustering. And this clustering, this approach, we group the grid based on the similarity, including the distance and the density based on the K-mean approach. So we can determine the area stratification based on the density and the distance and the density. And we including the two weighting variable, which is the W equal 1 and the W equal to 0.1. And in the W equal to 1 scenario, which means the equal weighting to the density and the distance. So you can see that this is the result of the area stratification. And when we decreasing the weighting, which means the spatial 0.1, and which means that in this approach is less weighting to the distance. So you can see the area stratification has become more patchy compared to the spatial 1 approach. And the next, we consider the other approach, the other thinking of the area stratification by using the SPDE approach. And actually, this is no area stratification in this approach. It uses the continuous Gaussian random field to represent the spatial variation. And this study, I use the VEST model to conduct this analysis. And this model is developed by the James, and he's here. Okay. So, and in this approach, they use the mesh to made for a mesh to approximate the spatial variation in the space, because this is the continuous variable. So they use the mesh to approximate the spatial variation. And also this method can consider the spatial correlation, which means we can the correlation can depending on the distance. So if the distance increase, the correlation between the two station will become decreased. And also this method can consider the isotropic and anisotrophic effect, which means you can consider the direction of the spatial correlation. So next, because we want to understand which area stratification is the best approach to the CPUE data, so we conduct the simulation testing in this analysis. So in the first, we simulated the underlying true density distribution. And we try to examine the different the 5 spatial treatment in the GLMM model, which is the ad hoc approach, binary approach, and the spatial 1, spatial 0.1, and the VEST model. So you can see that in the VEST model, we use the mesh to figure out the spatial configuration to approximate the spatial variation in our study domain. And then because this is the simulation testing, so we can compare the different derived index from the different model and compare the performance with the true index. So this is the objective of this study. So we use the real world data and the simulated data of the Taiwanese deep-held deep-net fishery in the Northwestern Pacific. So this is the shape of the deep-held deep-net. And we have some questions. One is what is the best spatial treatment in the CPU standardization? And we consider the 5 approach, and these 4 approach is the spatial stratified approach, and the best doesn't have the area stratification. And the next, we want to explore the influence of the variable on the resulting standardized CPUE, and these details will be shown in the later slide. And finally, we want to evaluate the impact of the 2 spatial sampling patterns in the CPUE standardization, which is the random and the preferential sampling for the fishery data. So this is the model structure used in this study. So we all use the GLMM model to evaluating the several spatial treatment. So this is the spatially stratified approach. So this model consider the year, area, and the area is depending on the different method and the spatial temporal effect, which is the interaction between the year and the area effect. And this is the random effect. And we also consider the quantitative SST effect and the basal effect. And the basal effect is a random effect. Okay, so the same model structure also in the VEST model. So in the VEST model, we consider the spatial effect and the spatial temporal effect as the random effect. And the same model structure, the basal effect and the quantitative SST effect also considered in the VEST model. So this is the result from the real world data from the derived index from the different methods, and the black point is the nominal CPUE. And you can see that the general, the abundance of the Pacific saury show the fluctuating pattern. But we noticed that in the 2009 to the 2012, this is the inconsistent trend among the different methods. Okay, so we also conduct some cross validation to compare the different performance between the different methods. And in general, the better model can perform the best based on the cross validation analysis. So next, so in the past, we most CPU standardization just understanding the the experience variation for each variable, and they don't understand the configuration the confounding effects, how to affect the nominal CPUE. So which is like the CPUE standardization like a black box. You don't know how to make each variable to affect the nominal CPUE. So the Bentley in the 2012 to develop a method to which is the inference plot and the matrix to understand the difference between the nominal and the standardized CPUE. So we can use we can see the data composition for this variable, for example, the vessel variable, and each vessel variable, the data distribution over the year. And we can get the coefficient, okay, from each vessel, yeah. And this coefficient can be standardized with between 1, yeah. So you can see that the coefficient is from the small to the big, yeah. And this coefficient is to match up with the data. And So we can further to calculate the annual influence. So which means we can understand according to the annual influence, we can understand in which year this variable how to affect the nominal CPUE to the standard CPUE. For example, if the annual influence is larger than 1, which means the standard CPUE is smaller than the nominal CPU. And if the annual influence is smaller than 1, which means the CPU is bigger than the nominal CPU. And yeah. So in summary, we can according to the influence plot to understand if the variable have a large coefficient and a substantial interannual variation of the data, which means this variable have the large variation of the annual influence. Yeah. So in the next slide, we will show the AI value for the each variable. Okay, so this slide is the comparison of the AI value for the each variable among the different methods. So you can see that the AI values vary across the 5 models for the spatial and the spatial temporal effect, while the vessel and the SST effect show the consistent trend among the GLMM. So this is highlight the importance of the spatial treatment in the models. Okay. And we can see that this is the very difference between the annual relative abundance index between the among the different methods in this period. And this inconsistent trend is because the AI value for the spatial temporal effect in this period is also not inconsistent. So this inconsistent affect this inconsistent pattern. Okay, sorry. And compared to the different variables, you can see that the spatial temporal effect can have the larger AI value. So this variable has the large influence compared to the other variable. Okay, so this is the real fishery data part, and now we move to the simulation testing. So as I mentioned before, we simulated the 2 base biomass for each breeder and the year. So we use the simple spatial temporal model, and we consider the year and the spatial random effect and the spatial temporal random effect, and we get the predict biomass for each breeder and the year, and we add some observation error to construct the underlying biomass distribution in our spatial domain. Okay, and now we simulated the 2 sampling scenario, and which is the random sampling and the preferential sampling. So we assign the probability of each grid based on the density. So we can control the phi value to determine the probability of the grid. So in the preferential sampling, the phi is equal to 8, which means the grid with the higher density tend to prefer to sample first. So you can see that in this map, this sampling can select the more grid with the higher density compared to a random sample. Okay, so the same process also do that. We apply the 5 GLMM model and compare the right index with the true index and measure some the performance indicator. So this is the result for the simulation testing. So this is the result from the random sampling. So as expected, the ad-hoc approach and the binary approach show the less precision, and the spatial clustering and the best show the higher precision and the lower bios. Okay, but in the preferential sampling, we found in the spatial 0.1, this model have the largest bias and a low precision. So which means the spatial 0.1 approach had the poorest performance under the preferential sampling. Is it because if we have the directional change in the fishing ground over time, and this method could not be very accurate to reflect the fish density over the time. Okay, so this is the I provide some summary and the fishery implication for my study. So according to the real data, real fishery data and the simulation analysis, the ad hoc manner and the binary approach may not can reflect the fish density distribution. But the base model can better explain the fish density than other GLMM. So, which means, which is because the fish density can vary continuous across the space, and the pattern in the density distribution over time can explained by the unmodeled spatial temporal variable. Okay, and for the spatial 0.1 may cause a substantial bias in the index estimation if the spatial temporal distribution of the fish fisher and the fish density is not random. And because the high density weighting may lead to some wrong area stratification. And so this may not be useful when there is a non-random distribution of the density or catchability. However, spatial one is the alternative method for defining the spatial strata if the best model is not possible. So in the general implication, we think our study, although this study is just focused on the Pacific saury, but the methodology should be accepted to the other fishery for which similar data are available. Okay, so this is the first topic of my study, and now let's move on to the second part, understanding the staff recruitment resilience based on the life history information. And as we know, the resilience of the staff recruitment, the resilience of the staff recruitment relationship, we usually use the steamness to reflect to related to the resilience of the fish, and this is related to the average productivity of the fishery resource. So in common, we use the Beverton and Hall equation to describe the relationship between the recruitment and the spawning stock biomass. And in the census in the 1992, he created a steamness he defined the steamness, and you can see that if the steamness is higher, which means the higher resilience, and if the steamness is lower, which means the lower resilience. So we can use the resilience to reflect the average fish productivity. Okay, so the steamness is based on the fish evaluation, ecology, and the reproductivity biology. So in the life history of the fish stock, the recruitment is the most component of the life history, the cycle of the life history. And the recruitment can determine by the survival of the early life stage and the fecundity from the spawning stock. So if we can understanding the survival of the early life stage and can understanding the spawning stock, the amount of the spawning stock, and we can understanding the recruitment is higher or lower. So the variability, the recruitment is influenced by the spawning biomass and the survival of the early life stage. And as we know, the changing life history parameter may impact the steamness because the estimation of the steamness is related to the life history parameter, and we have some evidence of the changing this parameter. For example, the growth due to the climate change could affect the fish productivity. So according to this paper, you can see that compared to in the whole time series, the LEPD has changed over the year. So this change could affect the fish productivity. So according to the other paper, we found that if we miss the classification of the stiffness. For example, this is the true value, but maybe we determine the stiffness in here, and the estimated SSD could be very different. So the stiffness is very important parameter in the star assessment, and have the substantial impact of the star assessment result. Okay, so this is the objective of this study. So because the Pacific saury is a very short-life species, and this species lack of the long-term recruitment, star recruitment data, so we lack of the knowledge about the variability of stiffness in the Pacific saury by the environmental change. So the objective of this study, the first one, we want to estimate the distribution of the stiffness value based on the available information on the life history under the stable environment. So we use the growth data, weight data, maturity data, and the natural mortality data, and assume the beaver-tail and whole recruitment assumption. And the next, we want to identify the relative importance of the life history parameters. So maybe the growth is more important than the natural mortality for estimating the stiffness. So we want to identify which parameter is most important. And finally, we want to evaluate the impact of the environmental change on the estimation of the stiffness. Okay, so we estimate the stiffness by using the A structure model, and this method is developed by the Mango in the 2010. And in this model, we use the beaver-tail and whole relationship. So the alpha, which means the slope at the origin, which is the recruitment divided by the spawning biomass. So you can see that if we have the different alpha value, which means if alpha is 0 lower, it means the lower recruitment potential. And if the alpha is higher, which means the higher recruitment potential. So we can use the alpha to get the stiffness value by including the SPR0, which is the expected surviving spawning biomass per recruit when there is no fishing effort. Okay, so in detail, as I mentioned before, the recruitment is the component between the spawning biomass and the recruit. So we can use this equation to calculate the recruitment and the spawning biomass based on the life history information. So we can in the upper component, we get the survival early life stage, and we can get the number of the spawning events, and we can understanding the vegetable constancy by the body mass, and we can get the alpha value for each population. So the survival rate before the recruitment and the spawning biomass can estimate by the information from the life history. And we also consider the uncertainty of each parameter to get the distribution of the stiffness value. So this is the process of this simulation data. So at the first, we simulated the A structure for the population J based on the individual age survival. And we consider the growth and the reproductivity parameter and the early life survival for the population J. And then next we calculate the total spawning biomass and the egg production of the population, and we can get the alpha value for each population. And finally, we can generate the frequency of the distribution of the limit. So we can repeat this process many times, and we can get the distribution of the stiffness. Okay, so we also consider the other parameter uncertainty, like the natural mortality, reproductivity, ecology, survival rate, and all uncertainty is assumed the log normal error with the CV is equal to 0.2. Okay, so this is the table for the literature review for the life history data for the Pacific saury. So the upper part is the information regarding to the spawning biomass. So you can see that the growth, the length weight relationship, the annual mortality, and the reproductivity ecology. And the most important, the lower part is the information for the recruitment. So this is the survival for the early life stage. Okay, so for the early life stage, the growth and the survival rate is the growth is assumed the exponential increase function to describe the growth during the early life stage. So we define the early life stage is about 120 days. Yeah, and this is from the egg to the larva. So this is the expected weight increasing among the during the early life stage. And we can use the empirical equation from the Marcour to understanding the natural mortality, even the body mass. You can use the equation to calculate the natural mortality, even body mass. Okay. So we compare the estimated natural mortality during the early life stage with the real level data for the Pacific saury. So the gray circle is the real data of the natural mortality for the saury. And then you can see that compared to the empirical equation, is very big. So we think this equation could be used into approximate the natural mortality of the saury larva. Okay, so this slide is the result of the estimated stiffness distribution. So this is the distribution we estimated from our analysis. So in the mean value is the 0.82, and the median value is larger is the 0.86. And in general, the distribution, the shape of the distribution was left square. So the mean value will smaller than the median value, and the confidence interval is within this range. And we compare the estimated limit from this analysis and compared to the global database, which is the fish life. And the fish life, the information from the fish life is 0.7. So it's very similar between the two estimation methods. Okay, so next, this slide is we want to understanding the relative importance of the life history parameter on the stiffness. So we calculated the elasticity for the stiffness, and it can provide a normalized measure of the effect, which is the 1% in the life history parameter value can change in the stiffness. So for example, if this is the infinity, and we increase the infinity from the 30 to the 33, if this parameter has a higher elasticity, so this change will be bigger compared to the lower elasticity of the stiffness, because the change is smaller. So which means if the parameter have the higher elasticity, it's more sensitivity. So this is the result for the relative importance of each parameter on the stiffness. So according to this result, we can see that the natural mortality as H0 and the maturity and the egg mortality, which could decreasing the thinness. And the natural mortality for the juvenile and the egg one, the effects very small, so it's the ignorable effect. But some growth parameter like the length-weight relationship and the infinity has the increasing effect on the thinness. Okay. So in general, the thinness of the saury is master sensitivity to increasing the growth, the body weight, and the survival of the egg and the larva stage. And okay, so this is the, so we want to further to understand the if we in the different environmental scenario, the thinness will change. So we want to understand the magnitude of the change of the thinness under the different climate scenario. So we reviewed a lot of the literature, and we found that if the climate change or the SFT increase, it would be affect the mean parameter value to maybe the 5% difference. So we assume if now is the good environment, so the growth, the length and weight, and the maturity will increase. The growth and the weight, length and weight relationship will increase about the 5%, and this maturity and the survival and the annual mortality will increase on the 5%. So we just adjust the mean value of the different life history parameter to reflect the different environmental condition. So we can calculate the different thinness distribution among the different environmental scenarios. So if now is the good environment, which means the SLT increase and this habitat is good for the saury survival, and the thinness will increase. So you can see that compared to the baseline scenario, the thinness is increased about 13%. But if now in the poor environment, so which means the growth increase, growth decrease, and the weight length increase, so which can lead to the smaller thinness. And so in the scenario 5, and this scenario 5 has the larger CV, and the larger CV lead to the slightly large thinness compared to the CV is equal to 0.2. So according to this results, we can see that the poor environment can substantially have the negative effect on the thinness of the saury, especially for the lower lower CV. And either the value or variation of the life history parameter could have an impact on the thinness under the potential environmental variability. Okay, so this is the summary and the fishery implication of this study. So according to this method, we found that the Pacific saury have the higher resilience to reduction in the spawning potential. So this the value is 0.82, and this value is very similar to the information from the fish life package. And the second, the thinness of the Pacific saury was monster sensitivity to the growth, body weight, and the early life stage, the survival of the early life stage. So it's very reasonable because the Pacific saury is the short life species. So the productivity is very related to this life history. And then we found that now is the poor environment, which could substantially decrease the resilience of the Pacific saury, which means the decreasing the growth, body weight, and the survival rate of the early life stage. And so in general, this study provides a approach for automating steaming of the other small pelagic fish when the life history data is available. Okay, so this is my final slide is the conclusion over the two topics. So the first one, we found the change in the abundance of the Pacific saury was mostly attributed to the unmodeled spatial temporal variable. So the simulation result also indicate the unmodeled spatial temporal variable could provide a more precise treatment to address the fish density. So it's because the unmodeled variable can explain for example, the non-stationary density effect and the monthly variation on the fish density and the biological interaction and some complicated oceanography effect over the preferential samples. So the unmodeled spatial temporal is very strong. It can maybe it can explain a lot of the things across the space. And the second study, we provide a numerical approach and based on the population biology, and this is the alternative way to automate the steaming because we didn't need to a long-term series of the flood recruitment data, and we can use this approach to automate the steaming. And because we consider the different environmental scenarios, and we highlight the non-stationary biological process which affected by the climate change, and it could influence the fish productivity and the potential affect the star system. And maybe this topic is my next step of my PhD result. Okay, so next this is the acknowledgement. So I want to thank my PhD supervisor EJ and Andre. Let me be here, and Nicholas, John Braja, and Kai Sang, and Mark Mango to provide the background information of the steaming. And I also want to thank the government of Taiwan to provide some money, and I can be here, and the NPFC to provide some opportunity to conduct the analysis for the Pacific zone. Yeah, that's all. Thank you.
Thank you, Jen. That was a really good talk. Now we have time for questions. And online people, you can type them into the Q&A. I have a question. It was like one of your first slides. It showed that China and Taiwan were catching more saury since 2010. Is that because like distribution change or moving off like Japan's EEZ or something like that?
Yes, you are correct. Because I think in the 2010, they have the highest effort in the high sea area because the China expand their fleets to harvest the Pacific saury. So maybe this is the one reason to lead to the decreasing catch of the Pacific saury after the 2010 because the higher effort in the high sea.
Okay. Thanks.
Yeah.
So
Sure.
it is said that the recent environment change in the North Pacific affects the biology of saury, like the migration route shifted to the eastward, and the new distribution area, the food availability is poor, so that's why it has a negative effect on the saury's growth. So can your model capture this kind of recent ocean environmental change? So I mean, so the ocean environment in the North Pacific dramatically changed in last 10 years, and that affects the saury's biology. It's my understanding. So can your model capture this recent change?
Yes, yes. Yeah, thank you for your question. Yeah, so because the distribution change across the space, and in the spatial temporal model, we including the model variable, which is the spatial variable. This is the random effect, and it can be different by each year. So you can use this effect to capture the unmodeled spatial temporal variable among over the year, and to maybe it can mimic the the spatial distribution shift of the density distribution or the migration. Yeah, I think so. This approach, yeah.
Thank you. Nice talk. I liked in your first topic that it seems like the approach that doesn't consider partitioning at all is the best one. And it's kind of what we were kind of talking about earlier as well. But I wonder of the approaches that do try and partition the areas, right? Have you tried to consider things like whether different fleets fish, and maybe they all fish in the same areas, so this doesn't matter, but I wonder if differences in the CPUE could be due to, like different fleets or different countries, I don't know, fishing separate areas of the range of these species, and if you could somehow use that prior knowledge when you do your area partitioning.
Oh. Yes, I agree with you. But yeah, for my case, the fleet is distributed to the whole spatial area. So we don't miss some situation you talk about, maybe some area they don't have the fishery. But yeah, I think this is a good point, because the vessel distribution over the space can use to do the area stratification. Yeah, because we don't have the fishery in this area, but we can get the information from this area. Yes.
And yeah, it's great talk. Thank you so much. Yeah, fishery CPUE analysis is really complicated for a lot of reasons, and it's cool to see the post-gratification results. Another topic that people talk about is how you subset the CPUE records to make sure it's kind of only the single fishery of saury. Like, I wonder if you could, I assume there's other fishing in the same area for tunas or other species, and there's a different set of models that people use to try to subset down to just the right set of CPUE records. Have you looked into that side at all, or is it just really clear in the case of saury that there's these ones that target it, and you wouldn't want to use these other fisheries in this spot?
Okay, yeah, thank you for your question. So yeah, you are correct. For example, for the tuna logbook data, they harvest the different species like the tuna, billfish, and the shark. So sometimes you have a lot of the target species and the bycatch species. But for the Pacific saury, this is the only target for the Pacific, so they use the hole to catch the saury. So the fishermen can research the position of the fish, the area which has the higher fish, and they just use the hole to catch the fish. So this is the target species fishery.
Yeah, that sounds like it makes it easier.
Yeah, because you don't have any, the bycatch issue or the zero fishing effort issue. Yeah.
Thank you, Jhen. That was very interesting. I was really interesting with the part 2. And I have maybe 2 questions for that. Could you maybe say again where did that come from for the experimental rate at the earlier life stage? Because those are like kind of very complicated data to get.
Okay. And yes, the information for the early life stage is very complicated and very difficult to get this information. And we use the empirical equation from the parkour. And this equation can provide the information for the natural mortality for the early life stage. And it's depending on the body mass. So if I can get the body weight for the lava, and I can get the natural mortality. Yes.
Which is for your species, right?
No, this is the
A global.
the global, maybe including a lot of the fish species and the marine species. Yeah. So this is the empirical equation.
And the,
But
the
we compare to the real world data for the Pacific saury because this person have some experience in the lab, and they can get the natural mortality value for the Pacific saury, and we compare this value with the empirical relationship. So you can see that it's very similar. So we think this equation can apply to the Pacific saury. Yes.
okay, I can get it. And so it's kind of surveying lava during the rain process. Okay.
You mean this?
Yeah.
Yes.
But-
Okay. So, but they just maybe have the 40 to the 60 days, really, and yeah.
Great content. I also come across the biological aspect and the variation of the eligibility level and 15 between the poor and the good condition.
Yes.
So it's the poor condition that but that 15 increase. So what is the biological rationale to and they grow smaller but they reduce
I think because I think in the good environment, the growth will increase. For example, the healthy can increase, then maybe the maturity can be become because this is based on the length, based on the size. So because in a good environment, the total healthy is increased, and it can which means this species can be more productivity, so it can have a lot of the productivity compared to the base environment. So I just to reduce the maturity depending on based on the length, so you can have the more probability to get the maturity because the length is decreased. So
I don't know the question was it is based on hypothesis or on some evidence.
yes, I have some literature review, and they can have this situation between the maturity and the growth, especially for the small pelagic fish. Yeah, so I just do this assumption between the growth and the maturity. Yes.
So you're just increasing or decreasing by 5% every time?
Yes, and yeah.
Cool. Well, if there's no more questions, let's give it up for Jen one more time. I think this is the first quant sem we've ended on time in a long time. So enjoy your weekends and get out of here.